Good afternoon, everybody. My name is Ramesh Giri. Today I'm presenting a poster on topic multispectral digital holography for microparticle characterizations. I'm from Kansas State University. 21st century is the era of development of science and technology. Out of many interesting things, the study of the micron-sized objects is one of them and is very important in many scientific fields like microbiology, environmental science, and climate science. Due to the advent of the instrument like microscope, it becomes easy to study and understand the objects which are not seen by our naked eyes. These tiny particles are really small but have a great influence in our daily life. The understanding of in situ aerosol particles here we are going to discuss are really important in many local and global climate models. But in many cases, due to the bulk size and complex structure of the microscope, it is not possible to image such small objects in their original locations without disturbing their structure. These problems can be solved by using a technique called the digital holography with an easy and efficient way. Since today digital holography is used to characterize the aerosol particles in terms of their size and shape, the knowledge of the material compositions observed with holography is limited. The color of any aerosol particles actually depends on the material compositions during its formations. Different aerosol particles reflect light according to their colors or material compositions. For instance, aerosol contains pure nitrates and sulfates reflect most of the sunlight. In conversely, black carbons absorbs most of it. Our objective here is to produce the color image of micron particles in order to investigate if particles of differing material compositions can be differentiated. For this, we perform an experiment where we use a multiple wavelength method in digital holography to record the RGB hologram of the micron particles. We use three primary color lasers, the red lasers of wavelength 633 nanometer, green laser 532 nanometer, and blue laser 430 nanometers. We, after special filtering and collimated these beams, we combine these beams by two dichroic mirrors, DCM1 and DCM2. The first dichroic mirror is used to combine red and green lasers, and the second dichroic mirrors combines all three color lasers and produce mostly a white light. This collimated white light is then passed through a chromatic lens, and then passed through a Michelson interferometers. Here we use a concave mirror CM to collimate the reference beams, and two polarizers we named as PP in the figure to balance the intensity of the reference beams according to the intensity of the object beams. The quantum efficiency of the color sensors we used is shown in the top right corner of the figure 1. We choose our lasers such a way that the crosstalk between the lasers in Bayer filters of CCD is minimum. Here the particles are placed on an anti-reflection window, its name as W in the figure, and thus the particles are stationary. So from our experiment, after recording the hologram by color CCD, a contrast hologram is obtained by subtracting a particle-free holograms which we call the reference hologram, from a hologram with particles we call the raw holograms. In figure 2, A is the contrast hologram of particles. The intention behind to get the contrast holograms here is to remove the background light effect and artifacts due to doors in the optical elements in the experiment setups. Finally, after reconstructions, this improves the quality of the image. The figure 2b is the RGB color channel separation of contrast holograms. These separate channels holograms are then reconstructed individually by using Fresnel-Kirchhoff diffraction theory. The image obtained from individual reconstructions are layered together and we get the color image in RGB color space. Here in figure 2c is the final color image of the particles, and figure 2d is the crops of figure 2c, and the figure 2e is the image of the same particles but obtained from the digital color microscope. Here to test our experiment further, we use a smaller particle with various colors. Here we present few color images. In figure 3, the left column images are obtained from the digital holography in our experiment, and the rightmost column are the images obtained from color microscope. The middle column shows the cropped part of the image within the white box as shown in figure. In conclusion, using 3 primary color lasers, red 633 nanometer, green 532 nanometer, and blue 430 nanometer in digital backscattering holography, we can produce the color image of the stationary microparticles. Future works. In future, the stationary particles will be replaced by free-flowing aerosol particles. For aerosols, the CW lasers will be replaced by pulse laser with pulse width less than 200 nanoseconds. We will study the color of the particles by analyzing its chromaticity. We will characterize them by their respective colors and categorize in terms of material compositions. These are few references where you can see how the digital holography works and what are the importance and what informations we can get from the digital holography. And we are funded from National Science Foundations and Air Force Office of Scientific Research. Thank you very much. I appreciate your attention. Please feel free to contact me if you have any questions. My email address is rgiri@phys.ksu.edu. Thank you.